In our previous lecture, we saw how to deal with circuits, resistor circuits that contain a single nonlinear component and constant sources, okay, constant independent voltage sources or constant independent current sources. Today we will extend that method or that analysis approach to cover the cases where the sources need not be constant. They're allowed to be time varying under the assumption that the value of the input signal, okay, the voltages or the currents provided by the sources, must remain close to its average value at all times. Okay, put another way, the DC component of the input signal must be must be sufficiently larger than the AC component. Okay. So we will study that circuits under the title Small Signal Analysis. So this is the case that we will cover today. A circuit with a nonlinear element and time varying input. Signal can be analyzed using the so-called small signal analysis method. Provided that if the magnitude of the AC component is small compared to the DC component. Is sufficiently smaller than the magnitude of the DC component, that of the DC component. Now, what we're talking about is the following circuit. Again, we have a nonlinear component and it's connected to a simple linear one port, or something more complicated but linear. Therefore, it always can be represented by its Thevenin equivalent, which would have the following form: the resistor, which is the Thevenin resistor, okay, resistance, and an independent voltage source. And now we represent that independent voltage source as two voltage sources connected in series. One of them is a battery, a constant voltage source that represents the DC component. The other is a time varying source which represents the AC component. Okay. And this is the topology that we will study. Again, let's call the constant voltage by E, capital E, and here we have ES of T, the AC component. Okay. This is the AC component, and here this is constant DC component. This is our LTI resistor with resistance R, and this rectangle is our nonlinear resistor. For which we assume that we know the terminal equation. Now, these are what we know according to this problem. we know the internal equation or the current voltage characteristics of the nonlinear resistor. And the AC component is such that its magnitude is always, at all times, sufficiently smaller than the DC voltage, which we denote by E. And what we're asked are the voltage and current of the nonlinear resistor. And we're not asked for them exactly. Okay. That would require solving the time-varying nonlinear equation. We're not interested in that. We're interested in an approximation of them. Okay. And if this condition is satisfied, then that approximation is an acceptable approximation. Therefore, it could serve as the answer to the problem. Okay. So how we approach this problem is as follows. What we're going to do is, we will, since this AC component is small, first we will ignore that and find the so-called zeroth approximation for the voltage and current. So that's what we already did in the previous lecture. Okay, once this time varying source is killed, we're left with a constant source and LTI resistor and our nonlinear element, and for that we know how to obtain the operating point. Okay. And then what we're going to do is, once the operating point is achieved, we're going to, using a linear approximation of this component around that operating point, we will obtain a linear circuit, and we're going to solve that linear circuit. It's called a small signal circuit, and from that small signal circuit we will obtain a time varying little correction to the operating point, and then that time varying piece plus the operating point voltage and or the operating point current will give us the approximate values for the voltage and current for the nonlinear element. Okay. So step 1 is therefore ignore the AC component of the overall input and obtain the so-called DC operating point. Okay. And that we know how to do from the previous lecture. Okay. Ignoring AC component means that killing it means replacing it with a short circuit. And once that's done, what we're left with is this constant voltage source E, the DC component. We have the LTI resistor here, and we have, because the input is constant, the solution, the nonlinear, the voltage and current of the nonlinear element are also constant, and those constants we denote by I0 and V0. Okay. So this circuit is what we're going to call the DC circuit for this problem. So this is our DC circuit. And in this DC circuit, we obtain I0 and V0 by solving the equation that we obtained earlier. And that equation is obtained by KVL and the terminal equation given for the nonlinear resistor. Okay. That is, we solve E equals R I0 plus V0. I0 is, in terms of V0, GB0, using the terminal equation for the nonlinear resistor. Okay, and writing KVL, the voltage provided by the DC source here must equal the voltage here plus the voltage of the nonlinear element. This is in terms of V0, assuming that G is known, and we can obtain a solution. Once V0 is obtained, the current is obtained by passing that V0 over or through that mapped to G. Then the DC operating point is I0 V0 equals G of V0 and V0. Okay, so that's step one. And if this is very, very small compared to DC component, then it may even be the case that we can stop here. This will be good enough approximation because V of t and I of t will almost be constants, okay, at V0 and GV0. There will be very, very little fluctuations with this ES of t, but if this is very, very tiny compared to E, those fluctuations can be ignored, and this you can take as your answer. But if this is not that small, then that approximation would be too crude. Okay, so you have to refine your answer a little bit, and in that case, what you can do is you can go one step further in the following way. That's step 2. Now here, this is zeroth order approximation. Now we're going to make this approximation a little bit better by adding a correction term to it. Now, since the magnitude of AC component, ES of t, is at all times small, by assumption, Vt, the voltage of the nonlinear element, is not exactly equal, but approximately equals to V0, the constant voltage that we obtained in the first step. For all t. That is, V of t will be in a small neighborhood of the constant voltage V0, or V of t will be in this interval V0 minus epsilon V0 plus epsilon, okay, for some small positive number, which we'll call epsilon, okay. It's not that important what epsilon actually is. All we have to know at this point is that it's something small compared to V0 at least. Then let's see what happens graphically. Okay, this is the IV curve. So let's see what happens to the voltage and current due to that AC component. Okay, now let's first visualize what's going on in step 1 once again. We did this already in the previous lecture. So what we have is, we have the low line. Okay. This is E, this is E over R. And this is the curve that represents R, terminal cohesion for the nonlinear resistor, and okay, I equals GV, and there those two curves meet or intersect. We call that point the operating point. And now in this problem, we're calling it the DC operating point. It's this. So the voltage corresponding to it is our DC operating voltage, which we call it V0. And the current corresponding to it is our DC operating current, which we call it I0. Okay. Now that's what happens when we have no AC component, or when we ignore the AC component. Now what happens if we introduce also the AC component into the picture? Okay. Now, without AC component, the voltage provided by the source is constant and E. Now with AC component, the voltage provided by the source, two sources combined, is E plus ES of t. Now ES of t is small, therefore this load line will be, depending on the value of ES of t, will be or the point that intersects the horizontal axis will be fluctuating around E. Okay. Now, since the slope of this load line is determined by R only, that fluctuation would mean that this load line will move back and forth, remaining parallel to itself at all times. Okay. Back and forth, and as it oscillates back and forth around E at that point and E over R at that point, remaining parallel to the original load line, it will intersect this terminal equation curve at different points. Okay? So, at some point in time where ES of t is positive and as large as it could be, this load line will extend as far as here, let's say. And at other times when ES of t is again large, but with negative sign, minus sign, the load line will extend to the other direction. Okay. So what's going to happen is the load line, now is it function of time, it will oscillate back and forth. Okay. Between those two border lines, let's say. And as it oscillates back and forth, it will at each time intersect the terminal equation curve, or the ID characteristics curve, which is constant, time invariant at different points. Okay. And here, for instance, we have V0 minus epsilon, more or less, and here, this point, the voltage of the nonlinear element will be a little bit larger than the DC operating point, which we're calling, let's say, V0 plus epsilon. Likewise, the current also fluctuates around the DC operating point, I0. Okay. Let's call this I0 plus something small and I0 minus something small. Okay, this omega and this omega, they don't have to be the same omega, but for the sake of simplicity, let's take it the same. Likewise, this epsilon and that epsilon, they don't have to be the same, but just for the sake of simplicity, suppose it's the same epsilon. Okay. So load line moves back and forth. But maintaining its slope at all times, slope is constant, forth, due to the AC component, ES of t. Okay. Now let's concentrate on what's going on here, okay? We have the DC operating point here, and then due to ES of t, load line moves back and forth, and as it moves back and forth, at each time it intersects I equals GV curve at a different point. Now if we enlarge that section of the graph, okay, what we're going to see is, here we have a piece of this nonlinear curve, but since it's confined to a very small area, that nonlinear curve we can approximate with a line. Okay. So here we have something. Here we have another line. See the load line. Okay, so this is I equals GE. Okay, the terminal equation curve, and this is the load line which moves back and forth. Like that. And as it moves back and forth, this point that intersects with I equals GV curve changes in time. This is the DC operating point, GV0, V0. Okay. Now, the observation that will help us analyze the circuit in a simple way is the following. This piece of this nonlinear curve, since it's confined to a very small area, can be very successfully approximated by a line. Okay? So this is, even though it's not a line in general, because it's a nonlinear curve, can be approximated by a line. So this is almost a line. Okay, at least in some neighborhood of the operating point. And that simple observation will help us obtain a very successful approximation for the voltage and current of the nonlinear resistor. Okay, so let's continue with our step 2. In step 1, we killed the AC source and we obtained the so-called DC circuit, and using the DC circuit we obtained the DC operating point, which is V0 and GV0. And then in step 2, we made the following observation, that because the S of t, the magnitude of the S of t is small enough, the solution V of t and I of t will be confined to some neighborhood of V0. And in that small tiny neighborhood, this curve, I equals GV curve, the terminal equation of the nonlinear resistor, can be represented by a line. Okay? And let's see what happens if we go with that approximation. So first order approximation of the curve GV, I equals GV around V equals V0 is the following. Now G of V approximately equals G of V0 plus the slope of this curve at the operating point, DC operating point, V0. Okay, dG over dB evaluated at V equals V0 times the deviation from the point at which we're performing the approximation, which is V minus V0. Okay, this is times. Now, to simplify our analysis, let us introduce some notation. Let us define Gm as dGdV equals V0. So this is the slope of the curve I equals GV. Okay. And what's the unit of the slope? G is current, V is voltage, current over voltage, volt amp over volt. Therefore, the unit for this constant is moles, okay, or 1 over Ohm. So Gm is the slope of the line tangent to I equals GV curve at V equals V0. Okay. That is, with our new approximation, we can write GV as GV0 plus the slope Gm, which is constant, because V0 is fixed and it's constant, times V minus V0. Okay. Now in this equation, V is a variable, whereas V0 and Gm, they are fixed. Okay. And this is a good enough of an approximation if V is close to V0 for V in V0 minus epsilon, V0 plus epsilon, in some neighborhood of V0. epsilon is something small. Okay. Now, using this approximation, let's try to figure out a better representation or better answer to voltage and current of the nonlinear element. Okay, now we can proceed as follows. What we have is E plus ES of t. So this is the overall voltage provided by the source, both DC component and AC component active. Okay. Now this voltage equals voltage drop across the linear resistor plus voltage drop across the nonlinear resistor, namely R times I, the current, and current is a function of voltage, G of V, plus the voltage of the nonlinear resistor. Okay. And now we know that V, the solution, is close to V0, DC operating point. Okay. And because V is close to V0, we have a good approximation of GB at that point. Okay, so GB equals this when V is close to V0. So therefore, let's replace GB with its approximation. So we can write E plus ES of t equals R times, instead of GB, we now going to write the approximation of GB. G V0 plus Gn V minus V0 plus V. Now since this is an approximation of GB, we no longer have equality, but we have approximate equality sign, okay, between the two sides. So what we did is, from going from this, going from this step to that step, is we replaced G of V with its approximation around V0, with its approximation. And the approximation is here. Then we can replace E with R GV0 plus V0, because RGV0 plus V0 equals E is the equation that we use to figure out V0. So that's the equation that that emerged when we construct the DC circuit. Okay. Plus EST approximately equals RGV0 plus RGN V minus V0 plus V. Okay. From this line to that line, we use the following equation: E equals RGV0 plus V0. Okay. This is the equation that we use to figure out V0. Okay. So it's in a sense the definition of V0. Now there will be a nice cancellation, RGV0 here and RGV0, they will cancel. And what's going to remain is, let's leave ES of t on the left hand side and throw everything else to the right hand side. And if you do that, we have RGN V minus V0 plus V minus V0. Okay. Note that V0 is fixed, but V is a function of time. It changes with respect to time. Okay. If you're not happy with this notation, you can just replace V with V of t. Okay. For simplicity, we don't write that. Okay. Now let us define or let us introduce a new notation, which is delta V, which is the difference between V of t and V0. This is fixed, this is time varying, therefore this is also time varying. This is the deviation of actual voltage around the DC operating point. Okay, i.e. this is the deviation of V of t around the fixed DC operating voltage. Okay, and then with our new notation, we have Es of t approximately equals R times Gm delta V plus delta V. Okay, let's call this equation 1. Now, equation 1 will suggest the following circuit. Equation 1 suggests the following circuit, which is linear. Okay. Where R is the resistance that we're given, and Gm is conductance of the following resistor. R Es of t, and here we have another LTI resistor with resistance Rn, and Rn is 1 over the conductance, and conductance is the slope of the curve I equals Gv at the DC operating point V equals V0. This voltage, let's call it delta V, and this current, let's call delta I. And delta I is related to delta V through the conductance. Okay. And this circuit is called AC circuit, or sometimes a small signal circuit. Now let's see why this equation suggests us to consider this circuit. And the reason is as follows: because this voltage, let's compute this voltage here. We have two LTI resistors connected in series. Therefore, we can compute this voltage by a simple voltage division. And this voltage equals this resistance divided by the overall resistance seen by the source times the source voltage. Okay. This resistance Rn is 1 over Gm, and then the overall resistance is R plus 1 over Gm times the voltage provided by the source. And if you reorganize that equation, it's no other than the equation that we obtained using the approximation of G at V equals V0. Es of t equals R Gm delta V plus delta V. This is same as equation 1. So that completes step 2. So step 1 was kill the AC source and figure out the DC operating point, I0 and V0. Step 2, obtain the AC circuit by evaluating the slope of G at V equals V0 DC operating point. Obtain the AC circuit or the small signal circuit, and by solving this very simple circuit, figure out delta V and delta I. Okay, the deviation of the voltage around V0, deviation of current around I0. And finally, in step 3, combine V0 or add to V0 this correction term delta V, or add to I0 this correction term delta I, and you will obtain a better approximation than the DC operating point. Okay, so that's the final step. Step 3, now V of t equals V0 plus delta V of t. This is constant, this is time varying. This is the approximate solution. For the voltage of t, nonlinear resistor. And I of t likewise is I0 plus delta I of t, and relation between delta I of t and delta V of t is given through this equation in terms of the conductance. And this is the approximate solution for the current of the nonlinear resistor I of t. Okay, now let's apply this approximation method to obtain a solution for the following nonlinear circuit with time varying source. Example. This is the circuit, and we're given the following about the circuit. R is 100 ohms, E is 10 volts, ES of t is sine of t volts. Now that the magnitude of the AC component is at most 10% of the DC component. Okay, so it's sufficiently small compared to the DC component, and the terminal equation for the nonlinear resistor is 0.03 V squared, or V positive, and 0 for V negative. Okay, so that terminal equation we already considered in the previous lecture. Okay. Now find approximately the current and voltage of the nonlinear component. And let's do it by the technique that we have just developed, that is small signal analysis. So we have 3 steps, basically 2 steps, because the third step is just adding 2 answers from the previous 2 steps. In step 1, what we do, we kill the AC component and solve for the DC circuit and find the operating point I0, V0. And in step 2, we figure out the slope of GV at the operating point, V equals V0, and that slope will give us the conductance of the resistance that we use in the AC circuit. With that resistance, and this R, we construct the AC circuit, which is composed of this ES of t, this input, this resistance, this resistor R, and the resistor whose resistance is coming from the evaluation of the slope, okay, or the 1 over the slope from the terminal equation. And we solve that AC circuit to figure out the variation of voltage and current around the DC operating point. And once those functions or those signals are computed, we at the very end combine the DC part and the AC part to obtain the first order approximation for the voltage, and likewise for the current. Okay. Step 1, solve the DC circuit. Ohms plus minus 10 10 volts. We just have E, and E is 10 volts. This is our 100 ohms, and V0, and this is I0. We already considered, we already solved this problem in our previous lecture, and the answer was 5/3 volts for V0 and 1/12 amps for I0. Okay. Now, how about the AC circuit? Okay. For that, all we need is the resistance of the resistor that will represent the nonlinear component. First, find Gm, the slope of the curve I equals GB at the DC operating point. Now, GB is 0.03 V squared. Okay, because the voltage is positive, and V0 is 5/3 volts. Therefore, Gm is dG dV, valued at equals V0. Okay, the derivative of G with respect to V is 0.06 V. 0.06 V, and V is V0, which is 5/3, so that's 0.1. We have to be careful about the units here. Gn is dG over dV. G is current, V is voltage, so it's current over voltage. Therefore, the unit is moles, okay, or Siemens. Now, once we have this conductance, it's now straightforward to obtain the AC circuit. Step 2, solve the AC circuit. Okay. Step 1 was solving the DC circuit. Now we're solving the AC circuit in step 2. And what's AC circuit? The AC circuit has the AC component as its only source, ES of t, which is sine of t. In our particular example, sine of t volts. This resistance remains the same, 100 ohms, and here we have another LTI resistor, whose resistance is, or whose conductance is 0.1 moles. Therefore, its resistance is 1/0.1, 10 ohms. Okay, and now using this very simple circuit, we figure out the variation of the voltage around the DC operating point. Likewise, variation of current around the DC operating current. Okay. Delta V of t by simple voltage division. Here we have 10 ohms, here we have 100 ohms. Therefore, 1/11 of the voltage provided by the voltage source is taken up by this resistor. Therefore, what we have is 1/11 sine t volts. And how about variation of the current? Okay, it's simply voltage divided by the resistance, or voltage multiplied by the conductance. 1/110 sine of t x. Okay, and the final step, step 3, is just combining DC voltage with the variation around DC operating point and DC current combined with the variation of the current around the DC operating point. Therefore, V of t not equals but almost equals V0 plus delta V of t. And for our example, it's 5/3 plus 1/11 psi t volts. Likewise, I of t equals I0 plus delta I of t, which is 1/12 plus 1/110